What do soda, blood, and baking soda have in common? Well, stay tuned and find out. Well, the CO2 in soda is also in our blood, as well as baking soda. Baking soda, or more specifically, bicarbonate ion and CO2 are involved in the buffer system, which keeps our blood at a pH of 7.4. If our blood pH drops below 6.8 or rises above 8.0, it's bad news. One important aspect of the bicarbonate CO2 blood buffer is an open system, in which the CO2 concentration remains constant. We exhale any excess CO2 produced by this reaction. So stop the video for a second and answer this question. In the HCO3 minus CO2 blood buffer system, what is the acid and what is the base? And here are the answers. So let's take a look at this reaction in more detail. The first thing we want to do is determine the equilibrium constant for this reaction. Remember that CO2 is the acid and HCO3 minus is the base. So stop the video and determine which one is equilibrium constant. Okay, so here's a hint. Add these two equations together and you'll get the equation we want. Convert pKa to Ka, multiply Ka by K2, and we'll get K4. This number tells us that not much CO2 reacts with H2O to form H plus and HCO3 minus. At the pH of blood, it turns out that the bicarbonate ion concentration is 0.024 molar. So stop the video and calculate the CO2 aqueous concentration. So here's how we use the Henderson-Hasselbalch equation to calculate the CO2 aqueous concentration. So here's our CO2 bicarbonate blood buffer system. We calculated Ka to be 7.9 times 10 minus 7 in the last slide. The pKa, which is minus log Ka, is equal to 6.1. Let's apply this reaction to the Henderson-Hasselbalch equation. So pH is equal to the pKa, which is 6.1, plus the log of the base, which is the HCO3 minus, divided by the acid, the CO2. So under blood conditions, let's plug in our numbers and solve for CO2. So let's see what happens to the blood buffer under acidosis conditions. So stop the video and calculate the pH of blood when 0.01 molar H plus is added, assuming that the blood buffer is a closed system, and then do the same calculation when it's an open system. So here's a hint, do an equilibrium calculation. So here are the answers. So here's our equilibrium calculation. Note that the initial concentration of CO2 is 0.0012 molar, for bicarbonate is 0.024 molar. We're adding 0.01 molar H plus. According to the Le principle, the reaction should shift toward the reactant side since we are adding product. So at equilibrium, here are the new concentrations of CO2 and HCO3 minus. And to calculate pH, we get a pH of 6.2, assuming the blood buffer is a closed system. Now, if we assume the blood buffer system is an open system, the CO2 concentration remains constant. So let's recalculate pH using the Henderson-Hasselbalch equation. When CO2 remains constant, note that the pH only drops to 7.16. So what this means is, don't hold your breath. You know, hemoglobin transports oxygen from our lungs to our tissues. Hemoglobin also buffers our blood. Hemoglobin is a protein, which means it's a weak acid. Note that there's two forms of hemoglobin, the deoxygenated form and the oxygenated form. Let's stop the video for just a second and answer this question. Which form of hemoglobin, the deoxygenated form or oxygenated form, is the stronger acid? So the answer is, look at pKa. Lower pKa means stronger acid, so the oxygenated form of hemoglobin is a stronger acid. Next, apply your knowledge of equilibrium principles to answer these questions. So stop the video and you'll feel great about your understanding of hemoglobin in our body. So here are the answers. In the first question, does the acid form or base form of hemoglobin have the higher affinity for oxygen? Looking at the equilibrium constant, the answer is the base form. Smaller k means more reactants and less products, so the base form of hemoglobin holds on to oxygen better. For question B, note that hemoglobin is deoxygenated. In the acid dissociation equation, note that pKa equals 7.7. If we look at a titration curve, note that the blood pH of 7.4 is before the halfway point of 7.7, which equals the pKa. This tells us that there's more acid than base. We can also look at the Henderson-Hasselbalch equation. The ratio of base to acid is 0.5 to 1, so again, more acid than base. So hemoglobin has picked up oxygen in our lungs and transports it to our tissues. So in our tissues is the acid form or base form of oxygen and hemoglobin present. Again, let's take a look at the titration curve and the Henderson-Hasselbalch equation. The oxygenated form of hemoglobin has a pKa of 6.2. At pH 7.4, that's way past the halfway point. That means there will be more base than acid. The Henderson-Hasselbalch equation confirms this value. Note that there's 20 times more base than acid. In our tissues, this form of hemoglobin is present as we discussed in the last question. In the tissues, O2 is released or removed. According to the Le Chatelier's principle, that's going to shift this reaction toward the left. When HGB returns to our lungs, this reaction will get shifted toward HHGB. The acid form of hemoglobin picks up an oxygen, forms HHGbO2. That gets transported to our tissues, and the cycle continues. When we eat food, the respiration reaction occurs, and it produces CO2 in water. Now, the CO2 in water produces HCO3-, so it replenishes the HCO3-. That's how bicarbonate is replenished when we exhale CO2, which lowers the pH. Eating also produces H+, and that's going to shift this reaction toward HHGB. Now you know how soda, blood, and baking soda buffer our blood.